So we have problem number 5 in advanced classical mechanics practice final exam. Let's begin. Consider the Lagrangian L, parentheses, q sub 1, q sub 2, q sub 1 dot, q sub 2 dot. That's going to equal m over 2 times the quantity q sub 1 dot plus q sub 2 dot squared minus v times the quantity q sub 1 minus q sub 2. So part A, compute the canonical momenta. Part B, determine whether the Lagrange transformation is invertible. Part C, identify the primary constraint in phase space. Part D, construct the Hamiltonian on the constrained surface. And Part E, explain the physical meaning of the degeneracy. Okay, so we have the Lagrange. Some pronounce it Legendre. I've heard it mostly pronounced Lagrange. Some professors pronounced it Legendre. However, we'll say Lagrange. Transform in singular Lagrangians, and pardon me for my mispronunciations. So the Lagrangian is L q sub 1, q sub 2, q sub 1 dot, q sub 2 dot, and that equals m over 2 quantity q sub 1 dot plus q sub 2 dot squared minus v of q sub 1 minus q sub 2. The canonical momenta are p sub 1 equal the partial derivative of L with respect to q dot sub 1 equals m times q sub 1 dot plus q sub 2 dot, and p sub 2 equals the partial derivative of L with respect to q sub 2 dot, and that equals m times the quantity q sub 1 dot plus q sub 2 dot. So that's for part A. Moving to part B. So again, Lagrange transformation, seeing if it's invertible. So p sub 1 equals p sub 2. So the primary constraint is chi equals p sub 1 minus p sub 2 equals 0. The Hessian matrix is w sub ij equals this partial derivative here, partial second derivative rather, respect to L of L, partial second derivative of L with respect to this q dot sub I, q dot sub j, and that equals m times the matrix first row 1 1, second row 1 1. So the determinant here of this w is just going to be m squared times 1 minus 1, which comes out to be 0. So the Lagrange transform is not invertible, so we could say the Lagrangian is singular. So that's part B. And again, pardon me for any mispronunciation. That's definitely not a strength of mine. I do not know how to pronounce a lot of words. As far as in languages, I do not know. So part C, let's move along here, and at least properly. So, but the physics and the math is okay. So here, let v equal q sub 1 dot plus q sub 2 dot, and then p sub 1 equals p sub 2 equals mv. A symmetric way to write v in terms of momenta is v equals p sub 1 plus p sub 2 over 2m. The canonical Hamiltonian is h sub c equals p sub 1, q sub 1 dot plus p sub 2, q sub 2 dot minus L. And using the constraint p sub 1 equals p sub 2, p sub 1 q sub 1 dot plus p sub 2 q sub 2 dot equals p sub 1 times the quantity q sub 1 dot plus q sub 2 dot. Since p sub 1 equals mv, h sub c equals mv squared minus the quantity m over 2 v squared minus v times the quantity q sub 1 minus q sub 2. Close parentheses there. So h sub c equals m over 2 v squared plus v times the quantity q sub 1 minus q sub 2. So using v equals p sub 1 plus p sub 2 over 2m, then we could say h sub c equals the quantity p sub 1 plus p sub 2 squared over 8m plus v times the quantity q sub 1 minus q sub 2. So on the constrained surface, p sub 1 equals p sub 2 equals p. This becomes h sub c equals p squared over 2m plus v times the quantity q sub 1 minus q sub 2. From there, we could say that the total Hamiltonian h sub t equals the quantity p sub 1 plus p sub 2 squared over 8m plus v times the quantity q sub 1 minus q sub 2 plus u of t times the quantity p sub 1 minus p sub 2, where u of t is an arbitrary multiplier reflecting the non-invertibility of the Lagrange transform. And a subtle but important consistency check is that the primary constraint must be preserved in time. Okay, so we have this Poisson of bracket of chi and h sub t equals 0, and since chi equals p sub 1 minus p sub 2, and h sub t equals the quantity p sub 1 plus p sub 2 squared over 8m plus v times quantity q sub 1 minus q sub 2 plus u times the quantity p sub 1 minus p sub 2. My apologies for that condensed space there. So then here, chi dot equals negative 2v prime times the quantity q sub 1 minus q sub 2. So the consistency requires this secondary constraint here, v prime times q sub 1. So v prime q sub 1 minus q sub 2 equals 0. And unless the relative coordinate lies at an extremum of v, the singular system is dynamically constrained. The physical meaning is that the Lagrangian depends only on the sum of velocities q sub 1 dot plus q sub 2 dot, not on the difference of them, q sub 1 dot minus q sub 2 dot. So we could say one velocity combination is dynamically meaningful, while the other is undetermined by the kinetic term. The relative coordinate q sub 1 minus q sub 2 appears in the potential, but its velocity does not appear independently. So the degeneracy means that the dynamics contains a constraint. Therefore, we could say only the collective velocity q sub 1 dot plus q sub 2 dot is kinetically determined. And a note over here, I should have mentioned this up further. The relative velocity is not independently determined by the kinetic term. And sorry for the way that is written, very condensed. And my apologies if I miscommunicated or mispronounced anything. Again, I am definitely not, I am not an expert in how to pronounce names. And my apologies again for any miscommunication. But thank you very much, and have a great day.